Purpose of this video is to go over the Metropolis algorithm. The Metropolis algorithm is a type of Markov chain Monte Carlo process, which in turn is a type of random walk. The mathematics underlying the Metropolis algorithm are shown in the appendix. And in the next video, we will apply the Metropolis algorithm to Bayes' theorem. To describe the Metropolis algorithm, I'm going to rely on a very clever example from Kruschke, in which he has a meandering or wandering politician that rules over a bunch of islands and wants to visit them with a frequency that is equal to the relative size of those populations. And so the way the algorithm is going to work is it will start off with a politician on a particular island. I'm going to refer to this as initialization. Politician begins on an initial island. As it turns out, it isn't going to really matter what island we initially put the politician on. So the politician visits that island next morning, wakes up, and needs to decide whether they're going to move to Island 1, move to Island 3, or remain on Island 2. So the first thing they got to decide is whether or not the proposed island is Island 1 or Island 3. To do that, they flip a coin, and if the coin comes up heads, we're going to consider moving to the island on the right-hand side. If it comes up tails, they're going to consider moving to the island on the left-hand side. So let's assume the politician flips the coin, turns out heads, so therefore they're going to be considering island number 3 as the proposed island. So now the question is, do they remain on island 2, the current island, or do they move to the proposed island, island number 3? To determine that, they begin by calculating the population ratio, population of the proposed island to the population of the current island. And if the ratio is greater than 1, then they move to the proposed island. So if we look at the size of these two circles, it looks like circle 3 is going to have a bigger population than circle 2. The ratio is greater than 1, so the politician moves. So the politician accepts the proposed island, moves to island number 3, which now becomes the current island. The next morning, the process is repeated. So the politician flips the coin. Let's say once again, they get ahead. Now the proposed island is island number 4. Once again, they calculate this ratio. But now, judging from the size of these circles, the proposed island has a smaller population than the current island. Let's say that that ratio is 0.9. Now, the way the Metropolis algorithm works is that what's meant to happen is that the politician should have a 90% chance of accepting the proposed island and moving to island number 4, or rejecting the proposed island and remaining on the current island. That should occur with a probability of 0.1. So how is the politician going to execute this? The way they're going to execute this is there's a number line that goes from 0 to 1. And there is the value 0.9. So we can imagine a uniform distribution across this number line. The politician can use R to get a randomly generated number from a uniform distribution that goes from 0 to 1. Then what they're going to do is they're going to compare the ratio to that randomly generated number. And if the ratio is greater than the randomly generated number, then they're going to accept the proposed island and move. Alternatively, if the ratio is less than the randomly generated number, then they're going to remain on that island. So that's the algorithm that they're going to use. At each step along the way, they keep track of the current island. So they keep this running tally of the current island. So initially, the current island was island number 2. Then they moved to island number 3. Looks like they moved to island number 4. They remained on that island in the 4th iteration. You can see after 10 iterations, it looks like they've been lingering on islands 4 and 5. And the whole idea is that eventually, ultimately, with increasingly large number of iterations, the relative size of these visits is going to be the same as the relative size of the populations. And that's what's proven in the appendix. We consider this to be a Monte Carlo. Use the word Monte Carlo. Why do we use the Monte Carlo? Because of the randomness involved. And the randomness enters it in a couple of ways. First is the coin toss to determine whether the politician looks right or left. And then we've got this thing here, which we can refer to as our accept reject rule. Accept the proposed or reject the proposed and remain on current. And so what it says is the probability of moving is the lesser of two numbers, the number 1 or the ratio. So if this ratio is greater than 1, then the smaller of these two numbers is 1 and the politician moves. Otherwise, if the ratio is less than 1, then whether or not they move is determined by the random number generator value being compared to that ratio. So this is just a flow chart that shows all this. First step is initialization. So select the initial island, determine its population, then figure out what the proposed island is going to be and get its population. Compare the ratio of the proposed to the current. If the proposed island has a larger population than the current island, then the politician moves to the proposed island. It becomes a new current island. That current island is tallied, and the process repeats itself. Otherwise, if the ratio is less than 1, then they compare the ratio and the random number. And if the ratio is greater than the random number, then they move to the proposed island back here. Otherwise, if it's not, they remain on the current island, they tally that current island, and the process repeats itself. So, the proof of the mathematics behind this is in the appendix, and in the next video, we'll apply the Metropolis algorithm to Bayes' theorem.